Yeah, ladies and gentlemen, good morning. It's a great pleasure to have the opportunity to speak twice in the same morning. So for that, I'm really grateful to Maciek and Gediminas for this very kind of opportunity to present the experimental work in my laboratory. In particular, today, I'd like to present work done on fast atom transport at the quantum speed limit. So in this experiment, this is a very fresh new experiment we have been now carrying out at the University of Bonn, in which we manipulate atomic wave packets and we try to transport. So the aim and the goal of this experiment is to transport a wave packet from one location to another location in the minimal time that is allowed by the laws of quantum mechanics. So for realizing these experiments, we work in optical lattices with ultra-cold atoms. This is our basic setting, which in the simple realization, an optical lattice is originating from two counter-propagating laser beams, and atoms are trapped in regions of maxima of intensity. And what we see here is a fluorescence image of two cesium atoms acquired with our newly built experimental apparatus that features a high-resolution optical objective lens, in fact, quite state-of-the-art that we have built in our laboratories at the numerical aperture of 0.92. So when we think of optical lattices, we perhaps have in mind the dynamics in which particles are allowed to tunnel through potential barriers to achieve the localization of matter waves. And this is something that works well, and we understand it very well. Even myself, I had the opportunity to test how well this works during my doctoral studies, in which we dress the optical lattice with time modulation, and we stretch the wave function of ultra-cold atoms from the size of a single lattice site to the size of 1 millimeter scale, and then in an accordion effect, we allow the wave function to be refocused back to the original size. These experiments took, however, a long time. This dynamics of tunneling is rather slow, so to achieve this type of delocalization, it could even take of the order of 10, 20 seconds. So the reason for that is that the energy scale in optical lattices is essentially determined by the recoil energy that depends on fundamental constant and the mass of the particles. And the tunneling is typically of the order of a few milliseconds. So that's the price that we have to pay. That's also the reason why modern experiments now are moving towards lighter atomic species with a lighter mass, as this allows to speed up the tunneling process. And this is the case here. It's a representation, so it's a representative selection of modern experiments working with potassium or even better lithium that speed up the tunneling process. Now I'm posing the question whether it's possible to speed up the process even further, to achieve delocalization while completely going without tunneling that is the bottleneck in the dynamic. And I argue that this is possible if we rely on the principle of state-dependent optical potentials. So what we do here, we use two different polarization states of light, right and left-handed circularly polarized light, to discriminate between two internal states of cesium atoms. So these two states that we select are electron spin up and spin down of the outermost electron of cesium atom. And now, if we choose carefully the wavelength of our optical lattice potential, we can make such that atoms in electron spin down do perceive the attractive potential of left-handed circularly polarized photons, while atoms in electron spin up are attracted by right-handed circularly polarized photon in such a way that if we have an atom prepare initially in spin down state, and this is prepared in an optical standing wave that is a deep standing wave, even if we jiggle the standing wave around, there is no possibility for the atom to perform any tunneling. Perhaps here what can happen is that we excite some motional excitation inside the lattice potential well. If now we want to achieve delocalization of these matter waves, what we have learned to do over the years is to prepare a coherent superposition of two internal states and to overlap on top of the original optical standing wave of left-handed circularly polarized photons, second optical standing wave at this time of right-handed circularly polarized photons. And we have now the control to independently move and displace these two lattice potential in such a way that we can split the atom apart, delocalizing them. And we are not only confined to symmetric type of operation, but in general, we can do any type of operation and also by arbitrary distances. So this process can take place on a much faster time scale, and I will come to that now, and typically is several orders of magnitude faster than the millisecond or few millisecond time scale required in typical standard ultra-cold optical lattice experiment. The way we realize this for the experimentalists that are interested to know about the details, so at the heart of our experiment is a highly performing polarization synthesizer of light. So the way it goes is that we superimpose in space two light field components in different polarization state of light. So this is horizontally polarized, this is vertically polarized. They are combined in a Wallenstein prism. They are mode filters, so we clean the transverse mode by coupling them in the same polarization maintaining optical fiber, and these two laser field components are then transformed from vertical and horizontal polarization into right and left-handed circularly polarized states of light in such a way that then they interfere with a counter-propagating laser beam that contains both components, and this gives rise to two optical standing waves. Now, these two standing waves are neither stabilized nor controlled so far. So to achieve that, we extract a little portion of light that is used to realize two independent optical phase lock loop that allows us to stabilize the phase of each individual light field component in such a way that we learned this from standard textbooks. If we have a standing wave and we control the phase of one of the running wave, essentially this controls the position of our standing wave, and here we have two standing waves, so we control both phases. And what we have realized is here is a high precision, highly performing polarization synthesizer of light. One can think like that. In fact, here we can synthesize on demand any polarization state of light we desire by controlling these phases and the amplitudes. And actually, this is perhaps the most performing polarization synthesizer available around. And those experimentalists that work with polarization state of light know how hard it is to achieve precision of 0.1 degree in defining the polarization on the Poincare sphere. And what we do here, actually, we do this dynamically, so we can dial any polarization we want, and with a response time of 1 microsecond, essentially, we can prepare a polarization state of light on demand. And this translates in a position control of our optical standing waves at the level of 1 angstrom. So this gives us the control of the position of the standing wave with 1 angstrom precision. So the way we use these setups in the past years is to realize discrete time quantum walks, this natural application of this setup in which we create a superposition of spin up and down. We chain this operation together and we repeat them several times. And this gives us a dynamics that is very similar to what we heard this morning by Wolfgang Ketterle about spin-orbit coupling. So in fact, this motion here is dominated by spin-orbit coupling realized with this spin-dependent optical potential. And this a very powerful system allows us to study topological insulator materials, gauge fields, and etc. But this is not the subject of my talk today. What I want to talk about is how to transport atom fast at the quantum speed limit. So for doing this experiment, we are interested first in starting with atoms that are prepared in the lowest motional states. So we do use a cooling mechanism that is certainly familiar to many of you, that is a sideband cooling mechanism, with the particularity that we drive this transition with microwaves, and we follow a scheme that has been first proposed by Florian Mintert and Christoph Wunderlich that uses microwave even if there is no momentum transport here to induce sidebands, and then cycling, then in this case, if we work in a deep lattice as we do, so the atoms have a high probability to remain in the same state, so eventually they are pumped in a dark state and there simply remain. This is the typical sideband spectrum we see before cooling the atoms, simply prepare from a magneto-optical trap, and after we cool the atom, we already obtain 90%. If we do something a little bit better, we can reach 98% in preparing them down in the ground state, and we see this by the disappearance of the blue sideband when atoms are in the ground state, are effectively dark to the application of the microwave radiation, and therefore removed from the trap. Now, so I want to focus on the transport experiment we have been recently carrying out, and the goal is to start with atoms that have been prepared in the motional ground state, and we desire to transport them, for example, from this lattice site here to the adjacent one, and we want to find out a way to control spin-dependently this optical lattice by either shaking the amplitude or shaking the position in a way that at the end the wave function will be transferred on the adjacent lattice site. We do not want to rely on tunneling, and we want to make in such a way that if this happens this way, and the wave function is a little bit wiggling, this is not good. What we want to achieve is a wave function that at the end occupies the motional ground state. So our figure of merit for this transport is to optimize the fidelity defined as the modulus square of the overlap integral of the transported atoms with the atoms in the ground state. For starting, before introducing you to the results where we reach the quantum speed limit, I'd like to present a more intuitive type of approach to transport atoms, something that is already fast. Clearly, we do not want to use adiabatic transport. This would be boring and too slow. One way to go is simply this very simple transport that we call the linear bang-bang transport. So atoms are at a steady state, at rest, and then suddenly we give the first bang, we put them into motion. This is the position of the lattice, and at a certain point we stop the motion of the lattice, reach again a steady state. And actually it turns out that this simple, very simple transport mechanism already works well to some extent when we choose the duration of the transport to be a multiple integer of the harmonic oscillator trapping period. Why is that the case? And we get a better intuition into the problem if we look at the a video or animation of the Wigner function, how this evolves from the point of view of the reference frame that is co-moving together with the lattice potential. When we start and we give the first kick in momentum space, the Wigner function is displaced, then starts to evolve, and what we do in the experiment, we wait a certain time and then we give the second kick, and now we look for 2 revolutions of the Wigner function, and this evolves, and then here comes the second kick, and if we give it at the right time, we can refocus the motional excitation back to the ground state. But clearly, this phase space trajectory shows that are quite stretched, and this reveals the fact that we are indeed in anharmonic potentials, and this prevents the perfect refocusing of motional excitation. And you can also see here from the Wigner function that exhibits quite a dent. So this is the experimental realization in the experiment of this concept of the linear bang-bang type of transport. And so we see the points with error bars. These are experimental data. And the curve behind it, so this red curve, is our theoretical prediction based on solving the Schrödinger equation for the transport. This is, I'm sorry, this projector is cut. Obviously. So this is the duration in microseconds. Thank you for the question. This is the duration in microseconds of the transport. And I want to emphasize this point that this theoretical prediction is not a fit, but this is simply the calculation based on the Schrödinger equation without any free-fitting parameter. And this agreement surprised and astonished me the first time I've seen it. But it took quite some time, actually, to get here. And I don't want to tell you the whole story, but I want to emphasize one of the most important points was to establish a new detection technique that could allow us to directly measure the fidelity of the transport process. And by fidelity, as I defined, this is the probability probability of occupying the motional ground state. We want to read out the probability. The way we do this is to start, let's imagine we have an atom that has been transported and distributed over several motional excitation. Now, coherences are not important for us. We want to read out the populations. So what we do in the experiment, we drive a transition on the red sideband in such a way that if atoms are not in the ground state, they are coupled and transferred to the upper spin states, and then through a push-out pulse, these atoms are simply removed. And because this microwave coupling cannot be tuned resonant for all motional excitation, because they different Rabi frequencies, so we repeat this process about 10 times very fast in a sequence. And afterwards, we are left only with atoms that are in the ground state. And this we see in this typical spectrum with this technique. And what is interesting for us to consider is the height of this plateau when we tune our frequency on the red sideband of the microwave transition. And in such a way, here we see this is an experiment in which we transport the atom, and the atom have been excited, creating motional excitation. We clearly see that about 30% of the atoms remain in the motional ground state, while other 70% have been excited to higher state. And that's our detection technique that we use. We want to now use that to look even beyond the simple linear bang-bang transport, and particularly to make use of optimal control theory applied to this problem, and going through rather sophisticated numerical optimization of the Schrödinger equation. Optimal control theory predicts or tells us that this is, for this duration of about 13 microseconds, this is an ideal ramp for transporting atoms with high fidelity. The challenge number 2 is how to reproduce these ramps in our experiment. Clearly, this is, we cannot program, so everything is digitally controlled. However, we cannot simply program this ramp and hoping to obtain a faithful reproduction of the blue ramp. In fact, the system has a certain response on the time scale of microseconds. So what we have to do is to go through the convolution problem and to derive the violet curve that, if programmed into the experiment, then delivers us the yellow curve. And now I clean it up, and you can see that the blue is what we want to achieve, and the yellow is what we truly achieve. And we have an optical interferometer that is in the place where the atoms are, and we can clearly and precisely measure with angstrom precision what the atoms are experiencing in the transport. This is very precious type of information that we have to understand the transport dynamics. And if we do so, that's the results that we obtain. So these are, again, the experimental points after we have applied transport ramps that have been optimized with optimal control theory. And we see this for different realization of trapping depth potentials. And what we see is that there is, again, a very good agreement between the theoretical prediction and the experimental data. And we see that by going for deeper and deeper lattices, the transition point where the system stops to achieve high fidelity and then drops down suddenly becomes gets to shorter and shorter times. As we can expect, this is determined by the stiffness of the trapping potential that for this experiment we kept fixed. In each realization, the trapping potential has been kept fixed. It's interesting also to note there's little tails of fidelity shooting up for a very short time, and this is also clearly reproduced by our theory prediction, and this is something that we understand well. It's because when we transport atoms too fast, then there is a probability for atoms to simply remain in the lattice sites where they were standing and in the ground state. And this is the case, we transport atoms very fast. So very recently we went, so this is the comparison for the theory computed for 0 radial temperature, and our atoms in this first set of experiments were thermally distributed in the radial direction of the optical lattice, and we have been recently working to cool the atoms, and very preliminary results now coming from the last week. We see that by cooling the radial temperature by a factor 2, this has already very much improved in terms of pushing the transport time down to the quantum speed limit, and we can very nicely see, I believe, this transition transition from a system that is quantum controllable to the point that the system cannot be controlled anymore and we cannot achieve any more high fidelity. And this time we didn't stop to short time, but we look also for the realization of longer transport times. And this, I think, gives quite an impression of what can be done. And I think it's the first time in which a complex quantum system that goes beyond the two-level system has demonstrated that it's possible to drive it to the quantum speed limit, where it's observed this transition from fidelity 1 to drop down to fidelity 0. So now the time is running over. I'd like to just mention and emphasize or advertise that we recently finished building a new experimental apparatus where it demonstrates the physics of spin-dependent transport in 2 dimensions. The experiment I presented to you now are spin-dependent transport in 1 dimension, but now we have the capability of doing that also in 2 dimensions. And to conclude, I would like to acknowledge the team I've had the pleasure to work with, and in particular Manolo Rivera Lam, who carried out this experiment I presented to you, and he also has a poster he will be presenting. So Carsten Robens is now carrying out his postdoc in the group of Martin Zwerlein, and has been behind the realization and construction of the polarization synthesized optical lattices, and the collaboration from Antonio Negretti and Tommaso Calarco for the theory of optimal control, and the long-standing collaboration with Dieter Meschen. And I would like to thank you for your attention.